Our planet, Earth, is often called the blue marble because over 70% of its surface is covered by water. Yet, despite this vastness, a staggering more than 95% of our oceans remain unexplored. Think about that, we have better maps of Mars than we do of our own seafloor. This means the vast majority of Earth's largest living space is a complete mystery. Today, we'll explore why so much of this watery world remains unknown, and what incredible secrets might still be hiding in its profound depths. Before we dive into the challenges, let's define what we mean by the deep ocean. Generally, this refers to areas below 200 meters, where sunlight begins to fade dramatically. Below 1,000 meters, sunlight disappears entirely, plunging the ocean into perpetual darkness. This region is known as the aphotic zone, meaning without light. It's a world distinct from the familiar surface waters, presenting extreme conditions that make exploration incredibly difficult. Understanding this environment is key to appreciating the hurdles. The first, and perhaps most significant, obstacle to deep-sea exploration is immense pressure. For every 10 meters you descend into the ocean, the pressure increases by approximately 1 atmosphere. To put this into perspective, in the deepest parts of the ocean, such as the Mariana Trench, the pressure can exceed 1,000 atmospheres. This is equivalent to having 50 jumbo jets piled on top of you. Any equipment or vessel sent into these depths must be engineered to withstand this crushing force, a monumental design challenge. Beyond the shallow sunlit zone, the deep ocean exists in eternal night. This absolute darkness profoundly impacts life and exploration. Without sunlight, photosynthesis, the process plants use to create food, is impossible. This means the deep sea largely lacks plant life. Creatures here have adapted with extraordinary senses, developing bioluminescence, the ability to produce their own light, or possessing extremely large eyes to capture the faintest glow. Navigating and observing in this lightless world requires artificial illumination, complicating every mission. Below the warmer surface layers, ocean temperatures plummet to near freezing. Most of the deep ocean maintains a consistent temperature of around 0 to 4 degrees Celsius. This extreme cold poses significant challenges. It affects the performance of exploration equipment, causing batteries to drain faster and materials to become brittle. Delicate scientific instruments, and any human occupants in a submersible, must be kept warm, requiring complex insulation and heating systems, which add to the equipment's size, weight, and power demands. Despite advancements, the seafloor remains largely unmapped at high resolution. We have more detailed maps of the surfaces of Mars and Venus than we do of our own planet's underwater landscapes. Traditional sonar mapping from surface ships is effective, but it is slow and less precise in the deep, vast expanse below. Without accurate maps, exploring the deep ocean is akin to navigating an unknown continent blindfolded, making scientific surveys, targeted sampling, and even simply avoiding obstacles incredibly difficult. Our most advanced deep-sea vehicles, known as submersibles, still face significant technological limitations. They can only carry a finite amount of power, which restricts the duration of missions and the operation of lights, propulsion, and scientific instruments. The need for extremely robust, heavy materials to withstand high pressures also limits their maneuverability and the amount of scientific equipment, or payload, they can carry. Developing lighter, stronger, and more energy-efficient technologies is an ongoing challenge for engineers and scientists. Deep-sea exploration is an incredibly expensive endeavor. The costs of designing, building, and maintaining submersibles and specialized research vessels are astronomical. Furthermore, funding for long-term expeditions, which require highly skilled scientific and technical teams, demands enormous budgets. A single deep-sea mission can easily cost millions of dollars, creating a substantial financial barrier. This high cost severely limits the frequency and scope of exploration efforts, leaving vast areas untouched and unknown due to budget constraints. Perhaps the most fundamental reason for the unexplored nature of the deep ocean is its sheer, overwhelming scale. The deep ocean represents over 95% of Earth's total habitable space, a volume of water so immense it dwarfs all terrestrial environments combined. Trying to explore this colossal realm with our current limited resources is like attempting to survey an entire galaxy with a single telescope. The sheer size of the unexplored regions means we have truly only scratched the surface, glimpsing a tiny fraction of its potential wonders. Despite the formidable challenges, the potential for discovery in the deep ocean is immense. Scientists estimate that millions of species, from tiny microbes to large invertebrates and fish, are still unknown to us in these depths. Every time a new deep-sea expedition is launched, new organisms are identified, sometimes with bizarre adaptations to the extreme environment. These discoveries not only expand our understanding of biodiversity but also reveal life's incredible ability to adapt and thrive under conditions previously thought impossible. The deep ocean hosts unique ecosystems that operate entirely differently from those on the surface. These alien worlds thrive without sunlight, powered instead by chemical energy in a process called chemosynthesis. Notable examples include hydrothermal vents, volcanic fissures on the seafloor that release superheated, mineral-rich water, and cold seeps, where hydrocarbons or methane leak from the seabed. These environments support entire communities of life found nowhere else on Earth, fundamentally changing our understanding of how life originates and sustains itself. Hidden beneath the waves are colossal geological features that rival or surpass anything on land. This includes vast mountain ranges, canyons deeper than the Grand Canyon, and immense abyssal plains. For instance, the Mid-Ocean Ridge is the longest mountain range on Earth, stretching for over 65,000 kilometers, almost entirely submerged. These underwater landscapes play a crucial role in ocean currents, climate regulation, and the distribution of marine life, yet much of their detailed topography and geological activity remains largely unmapped and unstudied. The deep seabed is a potential repository of vast mineral resources, including valuable rare earth elements critical for modern electronics and green technologies. Beyond minerals, the unique biology of deep-sea organisms offers incredible genetic resources. Extremophile microbes in animals could hold compounds for new antibiotics, anti-cancer drugs, or enzymes for industrial applications. While the prospect of extracting these resources raises significant ethical and environmental concerns, their presence undoubtedly fuels interest in future deep-sea exploration and research. The stable and undisturbed environment of the deep ocean acts as a natural time capsule. It preserves ancient geological formations, fossils, and even living fossils species that have changed little over millions of years, offering direct links to Earth's distant past. Discoveries here provide crucial insights into our planet's history, the evolution of life, and how organisms adapted to extreme conditions over geological timescales. Some pristine areas could even hold direct evidence of the very earliest forms of life on Earth, hidden from surface disturbances. The deep ocean plays a critical, yet not fully understood, role in regulating global climate, cycling essential elements like carbon and nutrients, and driving vast ocean currents. These massive underwater currents move heat and nutrients around the globe, profoundly impacting surface weather patterns and marine productivity far beyond the deep. Understanding these complex deep-sea processes is not just academic, it's vital for accurately predicting future climate changes, managing marine ecosystems, and maintaining the overall health and stability of our entire planet. Despite the immense challenges, discoveries in the deep ocean are constantly being made. Just recently, researchers have identified new species of bioluminescent jellyfish, some with never-before-seen light patterns, and massive deep-sea coral reefs thriving in absolute darkness thousands of meters below the surface. These ongoing findings serve as powerful reminders of the incredible wonders and vital secrets that patiently await discovery in the vast, unexplored regions, fueling our drive and commitment to delve even deeper into the unknown. The future of deep-sea exploration increasingly relies on advanced robotics. Remotely operated vehicles, ROVs, controlled by pilots from surface ships, and autonomous underwater vehicles, AUVs, programmed to navigate and collect data independently, are becoming increasingly sophisticated. These robotic explorers can withstand extreme pressures, operate for extended periods without human risk, and gather vast amounts of data more efficiently than human-occupied submersibles. They are the vanguard, pushing the boundaries of what is possible in the deep. The monumental task of exploring the entire deep ocean is too vast for any single nation or institution to accomplish alone. International collaboration is absolutely crucial. Initiatives like the Nippon Foundation JEBCO Seabed 2030 project, which aims to map the entire ocean floor by the year 2030, exemplify this global partnership. By sharing resources, expertise, and critically collected data, these collaborations accelerate discovery, reduce redundant efforts, and ensure a more comprehensive understanding of our shared planetary heritage for everyone. Citizen science projects are beginning to contribute to ocean exploration, albeit indirectly for the deep sea. Public involvement often takes the form of analyzing vast datasets, identifying marine species from images, or even contributing to technological innovations that assist researchers. While direct deep-sea access for citizens is limited, public engagement plays a vital role in raising awareness, garnering support for scientific research, and inspiring the next generation of ocean explorers. Every contribution, big or small, helps push the boundaries of knowledge. The primary, overarching reason to explore the deep ocean is pure scientific curiosity and the imperative to understand our home planet. By unraveling its complex ecosystems, intricate geology, and unique chemistry, we gain fundamental insights into how Earth functions as a whole. This knowledge helps us piece together the planet's evolutionary past, understand its current processes, and crucially, predict its future, including our own place within this delicate and interconnected global system. It's about fundamental knowledge for humanity. Beyond scientific knowledge, discoveries in the deep sea hold the potential to yield significant tangible benefits for humanity. New extremophile organisms could lead to groundbreaking compounds for antibiotics, powerful anti-cancer drugs, or robust enzymes for industrial biofuels and sustainable processes. Furthermore, the advanced technologies developed for deep-sea exploration often have spin-off applications for other extreme environments, from space exploration to medicine, creating a ripple effect of innovation that benefits diverse sectors of our society. Crucially, exploring the deep ocean is vital for its protection and conservation. We cannot effectively conserve what we do not understand or even know exists. By documenting new species and ecosystems, we can identify vulnerable areas and advocate for the establishment of marine protected zones. This proactive approach helps to safeguard these pristine environments before human impacts, such as deep-sea mining, pollution, or climate change, cause irreversible damage. It is an act of responsible stewardship for Earth's largest, most enigmatic habitat. The deep ocean truly remains Earth's last great frontier. Its immense scale, combined with the crushing pressure, eternal darkness, and freezing temperatures, explains why so much of it remains unexplored. Yet, every new discovery reminds us of the incredible wonders and vital secrets it holds, secrets that could redefine life, Earth's history, and our future. As technology advances and global cooperation strengthens, we stand on the brink of unraveling more of its profound mysteries. The journey into the deep is far from over, and the greatest discoveries may still lie ahead.